Bismillahirrahmanirrahim. Welcome dear students to the platform of Quanta Publishers. This is lecture series Teach Yourself, and today we are going to discuss the next topic, which is about the vector product. In last lecture we have seen that vectors can be multiplied in two manners. One product is known as the scalar product, whereas the other product is known as the vector product. In scalar product, when the two vectors multiply with each other, the resultant will be a scalar quantity. That is why that product is known as the scalar product. But today we see that if the product of two vectors results in a vector quantity, then the product is called the vector product. Let us consider we have the two vectors, vector A and vector B, makes an angle theta with each other. Just like this, if we take here a vector A, this is a vector A, and here is a vector B, this is an angle theta between these two vectors. And now if we want to resolve vector B into its perpendicular component, draw a perpendicular line over here, and we will get the two components. One is B cos theta, and the second one here is B sin theta. And in scalar product, this B cos theta will play an important role, but in vector product the component B sin theta will play an important role. And in the mathematical equation you see over here, when there is a cross sign between the two vector quantities, vector A and B on the left hand side, then is equal to the magnitude of vector A, and second is the magnitude of vector B. And now we use the trigonometric ratio sine theta, which play an important role in the vector product. And you will see over here that there is a normal unit vector n, because in order to make the right hand side a vector quantity, we have to attach a normal unit vector over here. Then this equation will be balanced. Here you see that in the next diagram, if we multiply the vector A with the vector B, in this diagram you will see that if we multiply the vector A with the vector B, then A, it is written as A cross B. And by using a right hand rule, if we multiply this vector A with the vector B, another vector will generate that is represented by this normal unit vector along this direction. And if we turn it another way around and multiply vector B with the vector A, then what will happen? You will see that if we multiply vector B with the vector A in the opposite direction, then we can write the product as B cross A. And now the third vector will generate in the downward direction, representing the normal unit vector. Here we use the minus sign with this normal unit vector, because if the above direction is taken as positive, then downward direction is taken as negative. So from this we can conclude that A cross B is not equal to B cross A, because both will generate the two different results. Here are some examples of the vector product. The first example is the torque. Torque is a vector quantity and is defined as the cross product of force and the position vector R. You can see that torque is equal to R cross F. On the right hand side, both are the vector quantities with the cross sign, and on the left hand side, the torque will generate. This is also a vector quantity. And the second example is the cross product of position vector R and the angular velocity omega. If we multiply these two vectors, we will get another vector that is known as the linear velocity. And the third example is about the angular momentum, which is the cross product of position vector r and the linear momentum p. Then angular momentum will generate. Here are some characteristics regarding the vector product. The first one is, if we multiply A cross B, we will get a equation A B sine of theta and with the normal unit vector n. And if we multiply B with that of A, so we will get the equation BA sine of theta and again the normal unit vector. But here is the normal unit vector with the negative sign, because the direction of these two normal unit vectors are opposite to each other. So we can conclude that A cross B is not equal to B cross A. Or if we want to balance it, we can write it as, if A cross B is equal to B cross A, then we have to put the negative sign over here. So we can say that the vector product is non-commutative. And the second property, when the two vectors are parallel to each other. In parallel condition, the angle between the two vector is equal to 0. So by using this condition, we can write as A cross B is equal to A B sine of theta into normal unit vector. Replace the value of theta over here, that is 0 degree, and sine 0 is equal to 0. And the right hand side is totally become equal to 0. It means the vector product will vanish when the angle between the two vector is equal to 0. In terms of unit vector, we can write it as, if we multiply the I unit vector with the I unit vector and the J unit vector with the J unit vector and K cross K, then all of these three product will be equal to 0, because the angle formed between the two similar vectors is equal to 0, then their product will vanish. And the third property here is, the vector product of the two vector has maximum value when they are perpendicular to each other. In perpendicular condition, the angle formed between the two vector is equal to 90 degree. And plug in this 90 degree over here. Sine 90 is equal to 1, and now the product will become equal to A, B and the normal unit vector. If we choose the magnitude of normal unit vector is equal to 1, then the product will become equal to A and B. Or in case of the unit vector, we can write them as, here you see that if I, in terms of unit vector, here you will see that if you multiply the two vectors I and j, the third vector k will generate. And if you multiply j with the k, the third unit vector I will generate. And similar, k multiplied by I, then j will generate. This is a cyclic permutation. You can see in this diagram, if you multiply I with the j, then third vector k will generate, and if we multiply j with the k, then I will generate. This is a cyclic rotation. And on the other way around, if we change the direction, then we use the negative sign with this product. Here you will see that if j is crossed with I, then the resultant vector is k with a negative sign. And the same pattern, k multiplied by j results in minus I unit vector, and I cross k will result in minus j unit vector. And the fourth property is about, the vector product is distributive with respect to addition. Here you will see that if A is distributed among the two vectors B plus C, then we can write it as A cross B plus A cross C. And on the same side, we can see that A plus B cross C, that can be written as A cross C and B cross C with the plus sign in between. This property here in the form of rectangular components, if we take the rectangular components of vector A, that is AXI, AYJ and AZK, and the B vector has a component bxi, byj, and bzk. Then we can write them in determinant form by using the first row ijk, and then writing the first vector, that is right over here, ax, ay, and az, and then the second vector and its component are bx, by, and bz. We can open this determinant by using determinant properties. If we choose the first row and first column, then we can multiply ay with the bz and az with the by. This is the first bracket over here. And if we want to compute the second vector, that is j, so we can choose the second column and the first row, and now multiply ax with the bz and az with the bx. So this is the second bracket over here. And now if we want to compute the third vector k, so you can replace the first row and the third column, and now multiply ax with the by and ay with the bx. So we will get the third bracket over here. And you will see that the magnitude of A cross B is equal to the area of parallelogram as shown over here. If you multiply this vector A with this vector B, and you will see that in parallelogram these opposite sides are of same length. So this is a vector A, so this is also a vector A. And if this side is a vector B, then this side is also equal to vector B. And if we multiply A with the B, so we will get the complete area of that parallelogram. Thanks for watching. We will meet in the next lecture.